Hello and welcome to another presentation in the LADAL Opening Webinar Series 2021. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language Technology and Data Analysis Laboratory at the School of Languages and Cultures at the University of Queensland, Australia. Now, before we start, I'd like to read out an acknowledgement of country, which we do here in Australia to express respect and gratitude towards the Indigenous people of Australia. So I'd like to say that we as members of the University of Queensland acknowledge the traditional owners and their custodianship of the lands from which we are broadcasting this webinar. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connections to country. I'd also like to say that we recognise their valuable contributions to Australian and global society. Now, if you want to know more about LADAL and the resources we provide, please feel free to explore the LADAL website. The URL of the LADAL website is shown on the screen. No worries if you've missed any of our talks so far. Most of them are freely available on our LADAL YouTube channel. You can also find information about past and upcoming presentations in the LADAL Opening Webinar Series 2021 on the events subpage of the LADAL website. If you want to keep up with what's going on at LADAL, please feel free to follow us on Twitter or on Facebook. And if you have any questions, suggestions, or feedback, please feel free to contact us via email. And without further ado, it's a real pleasure to introduce today's speakers, Jaden Macklin-Cordes and Eric Round. Jaden is a postdoctoral researcher in linguistics at the CNRS Dynamics of Language Lab, Noumier University Lyon 2. He recently completed his PhD at the University of Queensland as a member of the Ancient Language Lab. Jaden specializes in historical linguistics and typology, particularly using phylogenetic and quantitative methods. Eric Round, our other speaker, is British Academy Global Professor of Linguistics at the Surrey Morphology Group at the University of Surrey in the UK, and Director of the Ancient Language Lab at the University of Queensland. His research focuses on linguistic evolution and typology, especially in the domains of morphology and phonology. Eric also specializes in the Tangic languages of Queensland and the phonologies of Australian Indigenous languages. So let me stop sharing now and hand over to our speakers.
Over to you, Jaden.
Cool, thank you. So thank you for coming, everyone. The title of our talk this evening is Phylogenetic Comparative Methods, What All the Fuss is About, and How to Use Them in Everyday Research. I'm Jaden, and Eric is my co-author. And just in case anyone is wondering, this picture I took somewhere in Lamington National Park, and you can see the mist is lifting over the forest of trees, just as we hope our talk will demystify phylogenetic tree methods. Cool. So we'll divide our talk into 4 parts. The introduction we've titled Phylogenetic Comparative Methods, What the Fuss is About. Then we'll go into some of the details about phylogenetic comparative methods in practice for typologists. Then we'll look at a phylogenetic typological case study. And for some final discussion, we'll talk a little bit about areality and application to application to worldwide studies across multiple language families. And we should just mention from the outset that tonight a topic that we're not covering in our talk tonight is actually how to infer trees in the first place, how trees are made. But we will mention a little bit more about that towards the end. So at this point, I'll hand over to Eric.
Okay. And if I look a little bit confused, it's because I see my screen, which is currently a couple of seconds ahead of yours. So I don't actually know if I'm racing ahead, but we are up to the next slide, right? Section 1.
Yes.
Good. Right, so we're going to begin with an introduction to phylogenetic comparative methods. And our point here is not just to tell you what they are, but to attempt to explain why they're a big deal. That is what all the fuss is about. So in this section, I'll speak about language comparison and diversity. I'll talk about the consequences of languages being related to one another. Technical term for that is phylogenetic autocorrelation. I'll talk about phylogenetic autocorrelation in the history of linguistic thought, phylogenetic autocorrelation in the history of biology, and then talk about how phylogenetic comparative methods were born, which was an insight by Joe Felsenstein a few decades ago. And then that happens in biology, but then I'll talk very briefly about phylogenetic comparative methods beyond biology. So linguists, as we know, compare languages in order to understand the diversity of human language. When we do that, the scientific interest lies not merely in the contingent facts of today's particular languages and language families. Rather, our goal is to characterize the nature of human language in general, using today's contingent empirical data as evidence. A complication when we do that is that these contingencies that I'm talking about include historical relatedness. Now, the consequences of historical relatedness are profound. To start at the intuitive level, so consider the 4 languages that I've got sitting over on the right, related as shown by a little tree. And the question is, what proportion of this language family is SOV? So literally, you could say 75%, because 75% of the languages are SOV. But then you might think, well, actually, only one of the 2 major branches here has SOV languages, so should I really be saying something less than 75%? The problem here is that many statistics assume independence of observations that we're doing statistics on, but real languages are just simply not independent. In fact, they're severely non-independent, which means even a statistical notion as simple as the proportion of will fail. And we see that when we feel a little bit uneasy about giving an answer to the question. Now, in technical parlance, the issue here is phylogenetic autocorrelation, the tendency of languages to show similarities due to their genealogical relatedness. Now, phylogenetic autocorrelation is common to many comparative fields of science. In comparative anthropology, it was recognized by Sir Francis Galton already in 1889. And so it's also often referred to as Galton's problem. So phylogenetic autocorrelation also affects analysis in comparative biology and, of course, linguistic typology. And in all 3 sciences, the initial response as people tried to grapple with this, to try to respond to phylogenetic autocorrelation, was the parallel but largely independent development in each of the sciences of balanced sampling. And it was only later that biology diverged methodologically with the discovery of phylogenetic comparative methods. And here, for reasons of time, we'll focus on linguistics and comparative biology. So let me start in familiar territory with a very short history of methods in linguistics. So in 1978, Bell argued that the then current procedures of sampling major genealogical units, such as, say, Germanic and Romance, was problematic because these units themselves, if we take all of the different units that we're sampling, actually have different levels of relatedness to one another. Perkins created a 50 language sample, an influential one, which also attempts to account for areal bias, though his sample didn't take Bell's concerns into account. Dreyer in 1989 emphasizes the problem of the unknown. What we currently regard as distinct language families this decade may in fact be genealogically related. And we might join them together later. And what's currently regarded as distinct areas might in fact be areally related at great time depths. Cecil and others after him have pointed out that there's a kind of lose-lose predicament in balanced sampling. So either we sample restrictively enough that we kind of get a sufficient level of independence between the languages, but then the sample size is so small that powerful statistics often won't work with it. Or we make the sample size sufficiently large, But then the languages start getting too dependent for the statistics to work, and it undermines the assumptions behind. And so there are attempts to get around this, and these include Nichols' 1992 hierarchical testing approach, which in which you have statistical tests applied first within large areas and then across them. Reichhoff and others since then with sampling sensitive to the number of languages inside a subgroup. Dreyer and Haspelmath try sampling that's sensitive to the typological diversity of the languages selected, and Bickel does something slightly different to that, where you collapse data points if they've got a lack of diversity amongst them. And I guess the point to take away from this is that linguists have been very busy and very innovative and creative, developing variants on balanced sampling in order to handle the problem of phylogenetic autocorrelation. Now let me turn to comparative biology, where we find virtually every development in linguistics invented independently, usually about a decade earlier. So Clattenbrock and Harvey, 1977, devised samples when the selection of species is guided by variation in the data. Compare Dreyer and Haspelmath 2013 and Bickel 2009. Baker and Parker construct samples that are sensitive to ecological areas, so compare Perkins, and then replicate their testing within and across them, compare Nichols. Harvey and Mace, 1982, devised methods to choose subgroups at just the right taxonomic level to strike a balance between sample size and independence, compare Seesaw. So in this common phase of development in linguistics and biology, we have balanced sampling for genealogy, including attempts to incorporate areality. We see a shared range of strategies developed to partly offset the inherent limitations of the approach, including its inability to achieve true independence, its generation of sample sizes that are too small for powerful statistics, and also we should remember its need to discard nearly all languages or all species from the data set. So if we're trying to cover the whole world, we typically pick out just 50 or 100 languages, discarding the other 7,000. The common underlying approach here is to take our data set of languages across the world or species across the world, and then change the data set to suit statistics. And this common phase of development, methodological development, ends with a new breakthrough in biology, which was, don't change the data to suit the statistics, change the statistics to suit the data. And those new statistics are phylogenetic comparative methods. So the breakthrough was made by Joe Felsenstein in 1985. And here we're describing a core part of it in a nutshell. When we look at a tree like this, all of the languages have dependencies with one another. So the phylogenetic autocorrelation that I've been talking about. But Felsenstein noticed divergences between languages can be independent if you pick them carefully. So consider languages A and B. They are far from independent from one another because they share much of their history, which hopefully by now is highlighted on the slide. Moreover, of that shared history that they have, a lot of it is also shared with the history that C has. And moreover, the history before the proto-language that I've labeled I is shared with all of the languages in the tree. So this is where their dependency is coming in. However, and this is the key bit, the divergence between languages A and B is solely contained to the period after proto-language G. No other language or proto-language shares that particular part of the history. So the divergence between A and B is independent of what's happening in the rest of the tree. So too is the divergence between D and E, and also between C and G, and so forth. So these divergences, when you select them carefully, you can't just do it between any pair, but you can pick them there to cover the whole tree. When you select them carefully with reference to the tree structure, constitute a set of independent observations to which statistics can then be applied with nice full power. And moreover, you'll notice that what I did here does not require throwing out any languages. So we can now use the full data set and do statistics on it when comparing across languages like this. Now, phylogenetic comparative methods have grown immensely since 1985. However, fundamentally, they all share with balanced sampling this common aim, which is to account for phylogenetic autocorrelation. But the difference is phylogenetic comparative methods actually solve that problem. So several decades after their discovery, they're now being taken up in linguistics. I'm sure you've all seen papers that use them. They might be a little bit mysterious. What motivates this talk from Jada and me is firstly that their fundamental relationship to sampling has really not got a lot of attention. It's quite underappreciated, but it's really important because they're doing the same job. They're trying to fix the same problem. And so phylogenetic comparative methods, balanced sampling, you should think of them together. And secondly, phylogenetic comparative methods, for whatever reason, often come across when you're reading about them as some kind of hyper-specialized, mysterious uber science, accessible to some sort of godlike researchers with supercomputers. But mostly though, they're not like that. Of course, there are some like that, but mostly though, they're not. And we'd like to talk about how linguists can actually use phylogenetic comparative methods in normal kind of research. So to summarize, taming phylogenetic autocorrelation begins with a common problem, which is inherently facing anthropology, biology, and linguistics. And in response to that problem, we see in the history of the disciplines a common period of development in which all three sciences develop methods of balanced sampling. And the progression is so similar that it actually could easily have been a linguist who discovered phylogenetic comparative methods, because we were all working on the same problems. As it happens, the breakthrough was made in biology by Felsenstein and his method, and those that have grown from it are the phylogenetic comparative methods. And they solve that common problem. And I'll just note that as we move on to the next section, there's a footnote here which is important. So phylogenetic comparative methods solve the problem of phylogenetic autocorrelation. They don't solve the additional and separate and tricky problem of areality. And so we'll return to this topic of areality towards the end of the talk. For now, though, our focus is going to narrow. We're focusing on phylogenetic autocorrelation.
Cool. So in that last section, Eric covered the role and nature of phylogeny in comparative methods and the importance of a phylogenetic comparative approach. But what does this look like for us in practice as working typologists? So in this section, I'll give a brief tour of a few key phylogenetic comparative methods and some related concepts. Firstly, I'll discuss phylogenetic signal, which essentially quantifies the degree that your data accords with a given hypothesis about the genealogy. And I'll note a range of methods for measuring phylogenetic signal. And then secondly, I'll discuss methods for calculating averages and proportions that are sensitive to phylogeny. Now, one thing about these methods is that they require a language phylogeny as a point of reference. And a natural question that comes up a lot in linguistics is what we should do when we're not so sure that the reference phylogeny is accurate. In other words, how do we deal with phylogenetic uncertainty? So I'll take a look at some approaches to that question in the final part of this section of the talk. And I don't want to get too bogged down in some of the details here. The goal of this section is really just to show that there are some relatively lightweight, easy to use methods for doing some common kind of basic statistical tasks that are phylogenetically informed. So by using phylogenetic comparative methods, these methods we're talking about here, it's possible to incorporate phylogenetic awareness into some of the common statistical workflows that linguistic typologists have to use all the time. So Eric spent some time in that last section discussing the concept of phylogenetic autocorrelation. The key notion of phylogenetic signal refers to the degree to which divergences in the data match what we would expect given some phylogeny. So a phylogeny, a tree, in other words, is a representation of a hypothesis about genealogy. So you can think of phylogenetic signal as asking, how does the data accord with a particular genealogical hypothesis? And thankfully, there's been a suite of statistical techniques introduced in the past couple of decades. So now it's possible to quantify this specifically. And it's also possible to test whether phylogenetic signal in a particular data set is statistically significant. So in other words, is the phylogenetic signal that we detect stronger than what we might get in a pure chance scenario in which the data had arisen completely independently from the phylogeny? So although the inner workings differ, the basic idea behind different methods for measuring phylogenetic signal is essentially the same. All these methods require fundamentally three things. Most straightforwardly, you need some language data that you're interested in testing for phylogenetic signal. And then secondly, you need a phylogeny of the languages that you're studying as a kind of yardstick to measure against. And then thirdly, by necessity, methods for measuring phylogenetic signal carry an assumption about the model of character evolution. We won't focus on this third step here in this talk, but feel free to ask us about it in question time if you're particularly interested in that aspect. So the next step is to take the divergences between languages in the data that you're interested in. And depending on the method, this might involve taking variances in the data, variance in phylogenetic independent contrasts that Eric mentioned before, or differences between adjacent tree tips. And then we see if they correlate with various phylogenetic distances between them. So in other words, do smaller differences correlate with smaller phylogenetic distances and vice versa? And then, as I mentioned, it's possible to test whether phylogenetic signal is is statistically significant. So just to be clear here, it's a computer that does most of this number crunching. So what's important for us as typologists is really to pay attention to those three ingredients at the top there and make sure that we're feeding the computer the best ingredients that we can. And then the statistical software handles the rest for us from that point. And we've provided some tutorial materials on the LADAL website to help guide you through this process. I'll speak a bit more about that at the end. So the statistical implementation for measuring phylogenetic signal is going to differ depending on the kind of linguistic data that you want to test. So I won't go into all the details here of all these statistics I've listed in this table. The point here is more just to show you what's out there. And as you can see, no matter what kind of comparative data you might be dealing with, there's almost certainly already a measure of phylogenetic signal waiting for you, ready to go. So you'll notice there that methods for continuous data have undergone the most development, and there are a number of statistics that already exist for measuring phylogenetic signal in continuous data. So by continuous data here, I mean variables that can take any value on a scale, like measuring distances or duration or frequencies, that kind of thing. And there's a great overview of different statistics with the strengths and weaknesses of each in the paper I've listed there by Munkmüller and others. And I've also listed a couple of examples of these statistics being used in linguistics. Binary examples can take one of two values, so yes or no, presence or absence, that sort of thing. And we'll see an example of that D statistic listed there in the next section of this talk. Categorical variables can take one of a limited a discrete set of values. So for example, the different word orders. And then there are a couple of statistics there for more complex data types. So that first one there by Zhong and others is for when you have a set of multiple related variables that you want to test together as a set, rather than just testing one variable all on its own. And finally, the last statistic there by Adams in 2014 is for multi-dimensional data, where there are multiple values that define a single variable. So not sure what a great linguistic example of this would actually be, but an example from biology is morphometric data, where, for example, you might have a set of measurements that taken together describe the shape of a skull. I'm not aware of linguistic studies that use those couple of more recent methods yet, so there's plenty of potential there. So let me turn next to the topic of averages, proportions, and sensitivity to phylogeny. So this topic matters because in typology, a perennial task is to characterize the frequencies of traits of interest among the world's languages. So if we look at tree A here, which is the same tree that Eric introduced earlier, what proportion of this family is SOV? Is it 75%? Is it 50%? How about tree B? Here, actually maybe around 50%, because the first three languages are so closely related. And then what about tree C? Here, even though the first three languages form a subgroup, all four languages have close to the same genealogical distance between them. So here, maybe you could say 75%. And in fact, there's a long literature on how to formulate principled proportions and averages that take phylogeny into account. And the methods, these methods take into account both the topology of a tree, so that is the hierarchical embedding of different subgroups, and the branch lengths in the tree. So if you look closely at trees A, B, and C here, actually the topology of all these trees is exactly the same. The only thing that differs here is the branch lengths. So before diving into phylogenetic methods specifically, it'll pay to remember that even in the non-phylogenetic world, the concept of an average can be defined in a few different ways. So just think of the differences between means, medians, modes, geometric means, harmonic means, and so on. So each of these have different properties. For instance, means are more sensitive to outliers than medians are. And similar issues concerning the variety of definitions and properties arise with phylogenetically sensitive averages and proportions as well. So what about averages that are sensitive to phylogeny? Well, one of the most foundational phylogenetic averages is this Acl method, also known as the phylogenetic mean. This mean can be quite sensitive to the specifics of the highest order branches in a tree. So that might be a cause for concern in linguistics, where the highest order branches of our family trees are often the least certain and the most debated. The branch manager method was designed specifically to be less sensitive to the highest order branches. So that might be an interesting alternative that linguists might like to consider. The most important point, though, is that there already exist principled methods that have been in use for decades. And at the end of the talk, we'll mention some more specific tools that will allow you to use them. As I mentioned earlier, one of the key ingredients you need for phylogenetic comparative methods is a phylogeny, which represents a hypothesis about genealogy. But you might wonder, well, what if the hypothesis is unclear or incomplete or subject to debate or doubt? Can phylogenetic comparative methods still be used? Yes, they can. However, these questions do illustrate that the fact that phylogenetic uncertainty is an essential consideration. And thankfully, there are a couple of ways of dealing with it, which I'll mention now. So something which can be a little surprising at first is a point that was made strongly by Joe Felsenstein, who Eric mentioned earlier. Namely, because the distribution of traits across languages is fundamentally causally linked to genealogy, then any technique that purports to be phylogeny-free will actually assume a tree covertly. To see this, imagine we're studying 6 languages and the true real-world genealogy of these 6 languages looks like this tree, tree A here. Imagine, however, that we don't know what this true phylogeny looks like. Instead, what we're working with is the best kind of partial idea of subgrouping that we've got, something more, looking more like this tree in B. So in this case, when we're working with tree B, should we say, well, we don't have a good enough reference phylogeny, and so we should just disregard phylogenetic methods completely? Well, the answer is no, because phylogeny is fundamental to the structure of the data in the real world. And so it means that if we disregard phylogeny, we are merely setting each language on an equal relative footing. And that, as Felsenstein emphasizes, is the same as assuming this phylogeny, tree C there, which is also known as a star phylogeny or a rake phylogeny. So even though tree B may be imperfect, it's almost certainly a better approximation of the true phylogeny in A compared to tree C. So if we were to assume tree C effectively, we'd just be throwing away the information that we do have and choosing a less viable hypothesis about genealogy. And there are some good simulation studies out there which have evaluated this and found that, yes, indeed, using a partial phylogeny works better than simply assuming a star phylogeny. Another scenario is that we have multiple phylogenies that represent multiple hypotheses about genealogy. And in this case, we can actually use multiple phylogenies to reflect phylogenetic uncertainty. So here, the best strategy is simply to calculate the result from your phylogenetic comparative method. For example, say we're estimating phylogenetic signal, and to do that for each of your trees. So this gives a distribution of results, and this will give an indication of the range of uncertainty in your measure. So rather than just testing phylogenetic signal once, we're testing phylogenetic signal again and again against each genealogical hypothesis that we've got. And so one situation where this is useful is where your trees come from modern methods of phylogenetic tree inference. And since these methods typically provide an output, which is a whole set of hundreds, if not thousands, of highly likely trees, yeah, this is a good way to go in that instance. So I've just talked about phylogenetic signal, how data accords with phylogeny, that is, with a hypothesis about genealogy. And then I talked about averages and proportions that are sensitive to a phylogeny. And finally, about uncertainty in phylogenies. So now I'll hand back to Eric for a case study.
Okay, so in the third section here, we're going to present a typological phylogenetic case study of the methods that we've just been talking about. So our empirical topic here is going to be the laminal place of articulation contrast in the phonologies of the Pama-Nyungan languages of Australia. So Australian languages and their phonologies contrast between 4 and 6 superlaryngeal places of articulation. So they'll have a bilabial place of articulation, dorsal velar. They'll then have either 1 or 2 apical places that are articulated with your tongue tip, and either 1 or 2 laminal places articulated with the tongue blade. So here we're going to focus on the laminals, and especially on whether or not languages have a contrast between 2 laminal places of articulation, or if they lack the contrast and just have 1 laminal place of articulation. And so in this case study, I'll start with some nice long-standing claims about Australian laminals. We'll then look at phylogenetic signal in binary variables, which record either the presence or the absence of that contrast. And then we'll ask, what is the genealogically sensitive proportion of Pama-Nyungan languages that have the laminal contrast? So we're asking for the proportion, but we're doing it taking into account the shape of the tree. Now, you'll recall from Jaden's section that questions about phylogenetic signal are questions about the distribution of features in the tree. Are the features distributed among the languages in a way that accords with the genealogy that we're considering? So here I'm going to be interested in the distribution across languages of this laminal contrast. So to begin with a very broad context, generally speaking, phonemic systems are inherited, with some modification perhaps from ancestral languages down into their descendants. Consequently, as a starting point, we can probably expect them to contain a considerable amount of phylogenetic signal. These are things that are being handed down phylogenetically. Well, in Australia, however, for the laminal contrast, it's long been supposed that this may not be the case. And you can see this by looking at a map. So this map here is showing you the geographic distribution of the laminal contrast across mainland Australia. So dark colors are where the contrast is absent, so where there's just 1 laminal place of articulation, and light is where the contrast is present. So there's a contrast between 2. And if you look at that geographic distribution, you see it's covering some nice, large, sort of contiguous swathes of the continent, and can appear to exhibit really very little regard for the boundaries of language families. And this is emphasized repeatedly in the literature on Australian phonological typology for at least 50 years. However, let me add in a little bit more detail. The second map that I'm showing here has the same information from the first one, but it now adds in the major subgroups of the Pama-Nyungan language family, which dominates. And you might find that the second map has a slightly different effect. Now you may see that the distribution of the laminal contrast is relatively neatly organized within major phylogenetic units across the continent. Now, for the remainder of the case study, I'm not going to look at all of Australia. I'm going to focus on just the big Pama-Nyungan language, which covers most of the continent. Sorry, the Pama-Nyungan language family that covers most of the continent. So the presence or absence of a laminal contrast is what I'm investigating, and that's a binary variable, is present or absent. And so to test for phylogenetic signal, we can use the D statistic, which was in Jaden's table from earlier. And to take account of the phylogenetic uncertainty that exists about the Pama-Nyungan tree, I'm going to calculate these statistics using 100 different versions of the Pama-Nyungan tree. So it's a 100 tree sample that has been generated using modern phylogenetic inference procedures. Now, to see an example of how this binary variable is distributed across the tree, here's just one of the many trees that I'll be looking at, and I've plotted its presence and absence there, and hopefully you can make out the fact that the presences in white and the absences in dark are very much clumped together on the tree. They're not scattered across it randomly at all. And that makes sense given what we were seeing on the map. It's the same kind of pattern, though this time I'm showing a lot more detail. So when we run the statistics with the 100 different trees, the 100 results are summarized in the table here in terms of the mean value we get. For example, for the D statistics, we get 100 of them. What's the mean value of the D statistic? And then I've given standard deviation as well. So to just run through it, the D statistic we get is well below 0. Now, the definition of the D statistic is such that if you get a result that's well below 0, this indicates that the distribution of the data is strongly phylogenetically clumped, which is no surprise, but now we've confirmed it statistically. We're not merely eyeballing a map or eyeballing a tree and saying, yeah, I reckon. This is a proper statistical test. So the hypothesis that the laminal contrast is randomly distributed is one of the hypotheses that we test statistically, and it's rejected with a very low p-value. The hypothesis that the data has phylogenetic signal is not rejected, which is to say, randomness is not a viable explanation for this data and its distribution, whereas phylogenetic signal is a viable explanation for the distribution of the data. Let me then turn to the question of what proportion of Pama-Nyungan languages has a laminal contrast. Well, we know to start with, if we just count them up, that the simple proportion of Pama-Nyungan languages with a laminal contrast is 157 divided by 216, which is 72.7%. But that's not taking into account the tree. And in the little toy examples we showed earlier, we were trying to communicate that intuition that the tree does matter. So we can take into account the tree. So to obtain genealogically sensitive proportions, we use both the ACL and the BM methods that Jaden introduced earlier. And since these methods take genealogy into account, we can also use each of them with the 100 different trees in order to, again, reflect our phylogenetic uncertainty. And the results are shown in the table. So the simple proportion was 0.727. If we use the ACL method, which, as Jaden said, can be particularly sensitive to the sort of highest level, deepest time branches in the tree, then the proportion is 0.76, plus or minus a bit. Using the BM method, which is designed to be less sensitive to those higher order branches, which we're often quite uncertain about, the proportion is 0.705 minus a little bit, plus or minus a little bit. So, again, this is not earth-shattering. We're not going to rush away and publish this in Science and Nature, but if you do want to know what the proportion of Pama-Nyungan languages is that has a laminal contrast, and you would like to take into account the imbalances that are in there due to genealogy, well, the answer can be calculated. And in percentage terms, the answer is it's in the low to mid 70s, depending on which measure you use. Why do I have a couple of different measures? Well, it goes back to that thing that Jaden said. Remember, you can, even if you're doing non-phylogenetic statistics, you could use a mean, you could use a median, and they're going to give you slightly different values. Well, that's what you're seeing here. Slightly different definitions of the phylogenetic average will give you slightly different values. But in this case, it's quite satisfyingly all sort of converging in that sort of low 70% area. So we now have an answer for the proportion, and the nice thing here is it's taking genealogy into account.
Cool.
And I'll hand back to Jaden.
Thanks. So in the final few minutes of our presentation, I'll sum up the territory that we've covered, and then I'll return to a couple of final topics. Those are the challenges of areality and the comparison of languages across multiple families. So we started with the long appreciated fact that languages are related phylogenetically. And this means we have to take into account phylogenetic autocorrelation when we're comparing data between different languages, such as we do in linguistic typology all the time. However, phylogenetic autocorrelation isn't unique to linguistics, and there's a long history of comparative biologists, anthropologists, and others all grappling with the same kinds of issues that we've been grappling with in linguistics for a really long time. And as it happens, the critical insights that led to phylogenetic comparative methods were developed in biology, but they solve a common problem to all these fields. And so you could imagine in some parallel universe, Joe Felsenstein of the world could be a linguist. In the next section, in the section that followed, I gave a bit of a whirlwind tour of some of the common phylogenetic comparative methods available. And the goal there was to show that regardless of the particular kinds of data that you might be dealing with in your own comparative work, there are a whole bunch of statistics all ready to go that can be built into typological analysis relatively easily. And then next, Eric took a few of those methods and put them to work, examining laminal contrasts in Pama-Nyungan languages. And he showed how the laminal contrast, which was previously assumed to be a largely aerial phenomenon, in fact contains a strong phylogenetic signal. So before we finish up, it would be remiss of us not to talk a little bit about the elephant in the room, which is aeriality. And one of the limitations of phylogenetic comparative methods is that they don't account well for horizontal transmission. There's not really any way around it. So that is, they can't account for similarities that languages share because of borrowing. Of course, borrowing between languages is very common, very expected, and yeah, a common part of language change. And so a common concern that we often hear is that because borrowing and aeriality is more widespread in linguistics than it is in biology, PCMs, phylogenetic comparative methods, are less useful or less valid in a linguistic context. So there's sort of no skirting our way around this. It's an important point. The inability to account for aeriality is a limitation of PCMs, and it's a genuinely hard problem to solve. So something to keep in mind here is that the reason aeriality hasn't been solved yet is not due to a lack of motivation or a lack of trying. Biologists also have issues with horizontal transmission, particularly in subfields like bacteriology. And there is already some work in this space in linguistics too. And I've mentioned on the slide there a couple of references to those developments. The reason it's so challenging largely comes down to the mathematical realities of it. So phylogenies are fundamentally pretty simple geometric objects. And that means that the mathematics of phylogenetic comparative methods are relatively straightforward. Historical networks, on the other hand, which also take into account geography, are just orders of magnitude more complex and also much, much more computationally demanding. Nevertheless, just because we would rightfully love to have a model that better accounts for aeriality, that's no reason to completely disregard PCMs altogether. They still provide an elegant solution to phylogenetic autocorrelation, even if they they aren't the silver bullet that solves all of our problems altogether. So I'll just quickly hand back to Eric at this point for the remainder of the discussion.
Okay, so now let me talk about another final topic, and I want to talk briefly about comparison across families. So as we've emphasized, phylogenetic comparative methods require a tree, a phylogeny, and that tree represents a hypothesis about genealogy. But what about comparison across language families, where each language family is its own tree, unconnected to the others? Or are they unconnected? And actually, this is where this question gets a little bit interesting. I think for most linguists, we'd be fairly satisfied that it's actually very likely that most, if not all, language families are ultimately historically connected. And they're connected somehow via deep time genealogies, but we just don't know how. We don't know what those genealogies are, but they do exist. Well, the fact that they exist, but we don't know about them, well, that's just phylogenetic uncertainty. One option for dealing with this, which is found in balanced sampling approaches, is to take our different language families and to assume that all of them are exactly equally unrelated to one another. And that entails a rake tree, like the one that we've got on the slide here, whose claim is, for example, that the genealogical distance between, say, Indo-European and Uralic is exactly the same as the distance between Indo-European and Pama-Nyungan. Surely, though, for many linguists, that's not what we actually believe. So a better option and a challenge that we think lies ahead for the discipline is to begin assembling estimates of what deep time links might actually be. Now that's very difficult. We're not saying that it's easy, but previously in linguistics, there's been a very understandable decision not to engage in this, because I think the expectation was don't posit a tree unless you're positing something which you believe was the history. But as we've said all the way through this talk, phylogenies in phylogenetic comparative methods should really be thought of as hypotheses. And even if we don't know what the actual deep time history is, we can certainly distinguish between more plausible and less plausible hypotheses. So if I just go out on a limb here, I would say that it's more plausible that Indo-European and Uralic are more closely related to one another and Pama-Nyungan distantly than Indo-European and Pama-Nyungan are closely related to and Uralic distantly. Now, I don't know that, but I think it's a more plausible hypothesis, and I could express that hypothesis in a tree. So this is something that linguists have not engaged in previously because we haven't really had cause to, but I think we're beginning to. And the more we try it, the better we'll get at it. And the point here will be to remember that trees are not hypotheses. They're not the truth, but they are hypotheses. And if we say that we're using no tree, no global tree that joins all of the languages together, chances are we're actually using the rake tree that I've got on the slide. So hypotheses, trees are hypotheses, they're not the truth. And as our hypotheses change and get better, that will entail that our results from phylogenetic methods will change and get better, but that's just as it should be. So maybe a little bit contentious at the end, but that is the, I think, the implications of phylogenetic comparative methods for how you compare across languages. And just remember, if anyone tells you that they've got a method which does not use a tree, chances are they're using the rake tree. So the talk we've just given is, for the most part, a very short and condensed version of a paper that's currently under review, and we hope it will come out soon in a highly reputable journal. It's not out yet, but if you'd like to get hold of it, please keep your eye either on our Twitter accounts, or if you can email us if you'd like to see the state that it's in at the moment. Like we say, we're hoping that it'll be approved very soon. In addition to that, there is a detailed tutorial, which as of this afternoon is available on the LADAL website. So if you don't know this, the LADAL website hosts a whole list of tutorials for computational methods in linguistics. Ours has now been added to it. And this tutorial covers key topics of how you can build and modify phylogenies from existing resources. So if you're wondering where would I get the trees from, we talk about it in that tutorial, and by the end of it, you will be able to get your hand on some trees. The tutorial also covers how to calculate these genealogically sensitive averages and proportions that we've been talking about. So if you take the tutorial, you will actually be able to do the kind of stuff that we've just been discussing. So in conclusion, phylogenetic comparative methods provide the most principled response to an inherent challenge in linguistics of language relatedness. And be a mysterious black box. They're methods like other methods, and they don't need to be a mysterious black box that only others can use. You can use them in your own research, and we encourage you to do so and try them out. And thank you very much for coming along to the talk.